All right, hello, welcome. Let's do some tangent plane and normal line practice. And I'm going to be working through multivariable calculus homework 2.4 for my class, and I'm not going to be doing the extra practice in this video. I might loop around and record that as a separate video. And so I'm just going to start with number one. This is only 4 problems, so it's not going to be a super robust set of examples. But okay, number one is find the tangent plane and normal line to z equals y over x. Okay, which I'm going to write as y times x to the negative 1, because I find that a little easier to work with. At the point 1, 2, 2. All right, so I've got my point. I'm going to need some partials, so maybe I will start taking some derivatives here. So dz dx is equal to, well, if I'm taking the derivative of this x with respect to x, it's going to be negative 1 x to the negative 2. So it'll be negative y x to the negative 2, because y is just a constant. And at the point I'm interested in, dz dx at 1, 2, 2, well, that's going to equal negative y, that's negative 2, times 1 to the negative 2 power. Well, any power of 1 is 1. So I'm going to say that's just going to be negative 2. Okay? And then dz dy is going to be just x to the negative 1. And dz dy at the point I'm interested in is just going to be 1, because it's going to be 1 to the negative first power. Okay, so 1, 2, 2 is equal to 1. Okay, now that I've got my point and my partials, I'm ready to write my equation of my tangent plane. Okay, so yeah, I've got enough room here. It'll be z minus the z coordinate of the point we know on the plane is equal to the partial with respect to x times x minus the x coordinate of the point we know on the plane plus zy, that'll just be 1 times y minus the y coordinate. Okay. So there we go. We have ourselves a tangent plane. Now if I want, yes, it's at a normal line. Okay, well, I know that the point is going to be the same. I'm going to still be using 1, 2, 2. What I need to do is I need to get a normal vector to that plane, and then that'll be the kind of the trajectory of my normal line. So what I'm going to do is I'm going to set this thing equal to 0. Okay, I'm going to say that to write it as a plane that's set to 0 would be negative 2 times x minus 1 plus 1 times y minus 2 minus 1 times z minus 2. Meaning that my normal vector is going to be the vector negative 2, 1, negative 1. Okay. And then my normal line is going to be, let's say, L of t equals, okay, my point is 1, 2, 2, so it starts off with 1, 2, 2. And then I'm going to add on negative 2t to the x coordinate, positive 1t to the y coordinate, and minus 1t to the z coordinate. Okay. And then there I've got myself a normal line. Okay. Let's see. Number 2, find the tangent plane and normal line to the next one. Okay, I might go a little faster on this one. Okay, I've got tangent plane and normal line to z equals log of square root of x squared plus y squared. Oh yes, we graphed this one in one of my classes yesterday and found it was a nostalgic shape. So what I'm going to do, I'm going to take some partials. I've got a point, 3, 4 log 5. I don't want to put that there. Okay, I'm going to need my partials. So zx would be 1 over that square root times the derivative of the log is going to be 1/2 x squared plus y squared to the negative 1/2. So that's, again, square root of x squared plus y squared in the denominator, then times the derivative of x squared plus y squared with respect to x, and that's going to be 2x. Okay, all this to say that this partial derivative is going to be x over x squared plus y squared. Okay? And then I can tell by the symmetry of this equation that zy is going to equal y divided by x squared plus y squared. If you don't see that, then you should go through the step with the layers of chain rule and everything and convince yourself. But I can see that it's going to be the same thing. And so zx at the point I'm interested in, it's 3, 4. So it's 3 divided by 25. So in our case, yeah, this is 3 over 25. And zy is going to be, well, I bet it's 4 over 25. Yeah, 4 over 9 plus 16. Okay, perfect. Now I've got my slopes. I'm going to write my tangent plane. That's going to be, what is it? I froze up on that. Z minus the z coordinate is equal to zx times x minus the x coordinate plus zy times y minus the y coordinate. Okay, there we got ourselves a tangent plane. Okay, the normal line computation is going to go exactly the same, so I'm just going to set up for it because I know what's going to happen. Right, I'm going to take this thing and I'm going to move it over here, and so its slope number will be -1. And so I've got my normal line equaling, all right, the x coordinate was 3, the y coordinate was 4, and the z coordinate was the log of 5. Okay, and then kind of my slope numbers are going to be 3/25, so 4/25. And then this one was minus t, because it's just going to have a -1. Okay. And that's a normal line. All right, number 3, find places where the tangent plane is horizontal. Okay. Well, horizontal tangent plane is going to be parallel to the xy plane. And the xy plane is the set of all points where z equals 0. So parallel will be z equals a constant as my tangent plane. And the only way I'm going to get that is with fx and fy both equaling 0. So I'm going to write down fx, and that's going to be -2x. Okay, that's promising, because I can pretty easily figure out what kind of x's are going to give me that. And fy is going to be -2y plus 6. Okay. And so I know that I need both of these things to be equal to 0 in order for the tangent plane to be horizontal. And so that'll give me, well, I need -2x equals 0. And I need -2y plus 6 to equal 0. But I can solve both of these equations. This is x equals 0 and y equals 3. Okay, and then realize, oh, x equals 0 and y equals 3, that's something that's definitely in the domain of my function. I just need to figure out what the z coordinate is. So z equals f of x and y, which is going to be f of 0 and 3. So 3 minus 0 squared minus y squared is -9, plus 6y is plus 18. So I've got, this is +9 plus 3 is 12. And so the point at which there's a horizontal tangent plane is 0, 3, 12. If I had to write the equation of the horizontal tangent plane, that would be the plane z equals 12. And what we're going to find out later is that this is a potential extremum on the graph. But I think that you might see that it's going to be the absolute maximum, because it's going to be kind of one of those like soft cones. Anyway, all right, number 4. This one is kind of a challenge question. S is a sphere with radius 9 centered at the origin. Okay. There's just, it's like a kind of a fact from geometry, really from probably your geometry class that you most likely have forgotten by now. And so 1, 4, 8, yeah, maybe that's up here. I'm not too concerned. What I'm saying is that this radius here, okay, this vector, because it's centered at the origin, this vector is orthogonal to the tangent plane, right? So I've got a normal vector is 1, 4, 8 to the tangent plane. And I've got the point at which it's tangent. Okay. So I can write the equation of the tangent plane pretty easily. Yeah, so if my point is 1, 4, 8 and my normal vector is 1, 4, 8, then this plane, P1, which is that, it's P1, right? Yeah. P1 is given by, okay, so the first normal vector coordinate is 1, so it's 1 times x minus 1 plus 4 times y minus 4, move that down, plus 8 times z minus 8 equals 0. It's point normal form. And so I've got that. I'm going to actually clean this up. So this is going to be x minus 1 plus 4y minus 16 plus 8z. And then I'm going to figure out what, so I got minus 1 and minus 16 is negative 17 and negative 64. And I'm going to just real quickly do that arithmetic. 17 and 64 is 81. Okay, and then I'm going to, so okay, that's going to be an equation for plane 1. Then I've got plane 2. Okay, that's over here at, I clicked away from my problem set, 4, 7, negative 4. Who knows, maybe it's back there, on the back side or something. Either way, we'll say that's 4, 7, negative 4. And so it's going to be 4 times x minus 4 plus 7 times y minus 7 minus 4 times z plus 4 is equal to 0. And so I'm going to say, all right, I've got 4x plus 7y minus 4z equaling, all right, I got negative 16 and negative 49. I need to do some computations. I just don't want to do this wrong. So it's like 16 plus 49. Minus 16. No, it's plus 16. It would be 81 again. All right. And now, if you are just joining me in multivariable calculus and weren't with me last semester, this might be a little unfamiliar, but that's why I labeled it a challenge problem. I got 2 equations and 3 variables. And we're looking for the intersection of 2 planes, which I know is going to be a line. Well, this kind of calls back to linear algebra, right? I'm going to solve this 2x3 system, and so I'm going to need a calculator to do that. I mean, not really. I'm sure we could do this by hand, but if I'm being honest, I'm in a bit of a hurry. I'm trying to get this done real quick, and so I'm going to go over here, and I'm going to call on matrix math. I'm going to row reduce this thing, or row reduce a matrix that I'm about to put in. So I'm going to put a matrix that is 2 rows, by 4 columns. I'm going to type in my coefficients. 1, 4, 8, 81. And then 4, 7, negative 4, and 81. It's going to row reduce it for me. And I'll get, hold on, why would I, hold on. Yeah, I think it had been too long since I've done some row reduction, right? And I'm going to say, all right, my solution is 1x minus 8z equals negative 27, and y plus 4z equals positive 27. So what I'm going to say is that x equals 8z minus 27, y equals 27 minus 4z, and z can be whatever it wants, like, say, t, right? Because that's what an equation for the line looks like. Okay, so once I've solved the system, and I'm going to say that the line of intersection is L of t equals, okay, well, we're going to need a point that they share. Hold on, let me think about how I'm going to find that quickly. I wasn't thinking. If I just, it'll be true for any value of z, right, which is going to become my time coordinate. And so just say what happens at t equals 0. So it would be 0, or negative 27, 27, and 0. So negative 27, 27, and 0 plus my, okay, well, z is going to be equal to t, so it'll just be 1t. And that's t, z equals t. 27 minus 4t, so I need my eraser. And this was 8z minus 27, so that would be negative 27 plus 8t. Okay, and that'll be an equation for the line of intersection. But this was not an example I did in class. This is just a challenge problem in case you were interested in something beyond the, kind of, hate to say it, but boring tangent plane and normal line problems. Okay, but I think that's enough examples for you. If you are really comfortable with all of those, then you're good to go. If you're not, do the extra practice and maybe look for me to record solutions on that sometime soon. Thanks for watching.